Now, the second thing that we want to discuss is linear regression. One downside of correlation analysis is that it does not tell us the slope of the linear relationship. From the copier sales example, the question is how many calls should the salespeople make to get one more sales? This is slope, or the relationship between the dependent variable and the independent variable. Linear regression helps us to find this slope as seen in this equation. Y hat, the dependent variable, is estimated by independent variable x. B, or beta, is the slope that we are seeking to obtain. A is the intercept. The slope can be derived by this formula: correlation times the standard deviation of y divided by the standard deviation of x. Y-intercept can be derived by this formula: the mean of the mean of y minus the mean of x. Let's go through an example. Here's the same example from the correlation. Again, it is the same data from the copier sales example. Data is given as it is, and we want to predict how many copiers a salesperson can sell when making 20 calls. Since we are assuming that there is only one factor or independent variable, we can go ahead and calculate the intercept and the slope by finding the mean of copiers sold, the mean of sales calls, the standard deviation of sales calls, the standard deviation of copiers sold, and finally the correlation between sales calls and copiers sold. You put them into the formula and you can find the simple linear regression. Here, what we found. The intercept is 18.94 if we just plug in the y bar, the mean of y, and minus the slope times x bar is this. And the slope can be found by correlation times standard deviation of y over standard deviation of x, and it gives you 1.18. So therefore, beta is 1.18 and alpha or intercept is 18.94. Once you do that, now you can use it for prediction. Y hat equals a plus bx, and we found that y hat equals 18.94 plus 1.18x, and plug 20 calls into x, and we find that y hat is roughly 42.63. So when you make 20 phone calls, you can make 42 um, sales of copiers. There was a linear regression. Now let's expand it to multiple linear regression. While simple regression considers only one variable, multiple regression takes a few variables into the equation simultaneously. Doing so, multiple regression seeks to determine linear relationship among independent variables. Here's the generalized formula of multiple regression. Y hat equals intercept plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus, it goes on, and beta k times xk. That's a general form of multiple linear regression. Just like the simple linear regression, we are interested in finding the slope of each independent variable here, beta 1 to beta k. Usually, statistical software is used to calculate the slopes because it can get quite complicated. In multiple linear regression, we should pay attention to a few important statistics such as R-square and coefficient table. Let us take an example and understand multiple linear regression together. In this slide, we see that data is collected that postulate the relationship between heating cost, and three independent variables, namely the mean daily outside temperature, the number of inches of insulation in the attic, and the age in the years of the furnace. Do they affect heating cost? If so, how much? Those are the subject of study in this multiple linear regression. Here is the result from Excel. Let us first write out the equation. To do so, look at the coefficient table. We can write y hat equals 427.19 minus 4.5 x1 minus 14.8 x2 plus 6.1 x3. And they are from these coefficients, right? Intercept corresponds to 427, so the intercept is 427. The coefficient of temperature is negative 4.5, and insulation is negative 14.8, age is 6.10, right? You see that. So here is the equation. And the second thing is interpreting R square. R square is over here 0.804. So 80.4% is the R square. And what does that mean? 80.4% of heating cost is explained by the three independent variables. That's what it means. 80.4% is really high. Out of 100%, 80% was explained by these three independent variables. So that's very high predictive power they have. So it is trustworthy for us to move on to the next step, interpreting the coefficient. Let's go back to this coefficient, and we see that there are t scores here, and the t values, usually if it is greater than 2.5 or less than negative 2.5, it is statistically significant. Temperature, its t value is negative 5.9, and insulation is negative 3.1, and age is 1.5. So we see that temperature and insurance are significant variables, but age is not as significant, and we can ignore that we can see. Now look at the sign of the coefficient. We see that temperature is negative 4.5. This means that temperature has a negative impact on heating price. The higher the temperature is, the lower the heating cost is. It makes sense, right? How about insulation? Insulation also has negative sign there, negative 14.8. This means that the thicker the insulation is in the attic, the lower heating cost it is going to be. Age has positive sign, meaning the more aged the furnace is, the more heating cost it will be. However, it's an insignificant variable, so we don't have to pay much attention to this age coefficient. Now, if you are done with that, you can use this equation for prediction. If your regression equation is trustworthy, you can plug those numbers for prediction. So in our case, let's plug 30 degrees of temperature and 5 inches of insulation and 10 years of furnace age into equation. Then we see that its expected heating cost is $276.56. So this is how you are going to extend linear simple regression to multiple regression and interpret that.